majority. Right? Actually, the first thing is always a majority. So I always have to return the label of the first thing I see at that point.
Suppose if we have a large stream of data, and if this condition does not fail, if this condition fails, and it wants to return anything, and if that element which it returns is again the data from the stream, then how will you know that that condition has failed? It might be true that it has failed.
Yeah, so you don't know. So you don't know if it failed. We'll extend this to something better where you can have a better guarantee on the failure possibility. So this is kind of a warm-up to the frequent items problem. Yeah, but that's a good point. If it fails, I can return the value 1, for instance, or 2, and it's not a majority, but that's okay. I didn't claim I was going to return anything if there's no majority. I can, if this is an election and no one's majority, someone maybe at random gets chosen. Right? I didn't claim random. That would be something slightly different. This would not give a random answer. Right? But it could be anyone. Right? Maybe it's whoever gets the last vote is more likely to get elected. Very strange elections in this case. Okay, so I claim this algorithm actually works. This algorithm solves the majority problem. So let's kind of see why. I only need to do anything if I have some element which is a majority. If I don't have any majority element, then the algorithm can do anything it wants. Right? So I just need to worry about if I do have a majority element. Okay, so to see why this works, that means that something was in the stream at least m over 2, or greater than m over 2 times. Right? So that means that every time I saw the element, either this step happened, if this step happened, and that means I have the label, I incremented my counter. If I incremented the counter more than m plus 2 times, then there are not enough decrements that could happen here. This is the only time the counter ever gets decreased. And that means that I can never decrease it enough if I'm able to increment it, m over 2 times. The other possibility is that I see it and I reach this state. Well, here I'm essentially incrementing the counter with the label again. This also counts as an increment. I end up with the right thing in the label, and I increment the counter from 0 to 1. Right? So if every time I see the element and it hits this part or this part of the if condition, then I've incremented my I've incremented my counter. So if I hit this condition, then that means that someone else's counter was decreased. Right? How many times can I possibly hit this condition?
Less than 5.
Yeah, less than m over 2 times. And for every time I did that, that meant that someone else's counter increased, and I didn't hit this state when I was currently keeping the true majority as a label. So that doesn't count against the ones that can decrement. So there's a little bit more complicated argument, and so hopefully. So how many people were convinced by that argument? Okay, so yeah, I don't think I did a good job. So let me give a slightly different argument. It's kind of giving away the next step a little bit. But let's say instead of having one counter and one label, I had an extra counter, C prime, and let me use a different color here. C prime and L prime, okay? So now instead of what happened, every time, so at the start, every time I see something, at the end of every round, I'm going to, so if I hit this else statement, then I'm going to set label label prime equals to AI and counter equals to 1. Counter prime equals to 1. Okay? And so now, if I hit C0, then I'm still going to do this. And if I hit the else statement, I'm also going to decrement C prime. Okay? So now, every time I'm decrementing, I'm always decrementing some element I've seen before. Either the one I just saw, or I'm going to decrease one I saw much earlier. Okay, so that means that for every element I see which is of the majority, it's this special element which is the majority, I can only decrease it if it's in C prime, I can decrease it here, or if it was in this label, or if it was already in the right label and I saw something else, right? But I can only, but I can't do both of these. Both of these will not decrement the same counter. Will not decrement for the same element, right? If it's the majority element and it's already in the label, then it can only do this one. If it's not in the label, it will do this one. So I can't. So these cannot both decrement the same element, and I can only do at most m total decrements. Because everything is either something that was already stored in the counter, or the thing just stored in the counter. Okay, so that means that there are at most m of these. So I can't. Okay, I'm seeing a gap in the argument I wanted to make. So I can only decrement it m times, but I can do it, put it in there m over 2 things. Okay, so I don't think that's a very good map. So ignore the thing I said about the red case. So I'm going to give you a more general algorithm, and this will be seen as a special case, and hopefully it'll be clear at that point. So I apologize for this faulty argument. Okay, but hopefully it's kind of intuitively clear why you can't decrement it too many times. Okay, so I want to do something like this, but now I want to keep track of, so I want to solve a fourth problem, and so this is going to be called, let's say, 1 over k frequent items. So what I want to do is report all j such that so what I want to do is at the end so I'm going to produce this value hat fj for all j n in n. And it's going to satisfy the following property. So fj, the true, so fj hat is going to be less than or equal to the true value. So it's not going to be more than the true count. And if I look at fj hat minus m over k, this is going to be less. Okay, so K is going to be some, so think of K as like an approximation value. So
J minus K,
yeah, thank you. This was 9. So this is the true count. So I'm gonna do this with K counters and K labels. Okay, so I only get K counters, I only get K labels. And I'm going to be able to return this for every value J. Now J is everything in this domain N, so this is a really big set. How can I possibly return an Fj hat for every value? So that satisfies this. So let's say that, so let me kind of examine this quantity here, right? So what is, I'm saying it's always less than or equal to the true value, but it's not too much less, right? It's greater than the true value minus a small thing. So let's say K was 10, okay? So what does this quantity mean? So this is 10% of the data, right? So I want to say I don't want to be off by more than 10% for any value. So how many different items can I have that are going to be greater than 10%? Have a count greater than 10%? Yes, only 9, right? So I can't have more than 10 items that are greater than, each individually has more than 10% of the vote. Unless maybe I'm in one of these third world countries where, they count votes a little bit strangely. But so this is the population, this is the percentage of the, this is the number of votes someone gets, right? So not more than 10 people can get more than 10% of all the votes. So that means that I only have to keep track of these 10 counters, and anything I don't have a counter for, I can assume is 0. And that this quantity will be less than 0, because the true count will be less than 10%. And so the larger I set K, the more accuracy I get. If I set it to 100, then basically this is within 1%. If it's 1,000, I set it within 1/10 of 1%. Okay? So that's what's going on with this quantity here. So this does make sense because everything I don't have a counter for, where I return a label as my estimate, I'm going to implicitly assume is 0.
That should be k-frequent items, right? The question. K-frequent items.
Yeah, so sometimes this is called, so often it's called like epsilon approximate frequent items, and 1/k is set to epsilon. So then that would be epsilon times n, where epsilon is your percentage error. But that just ends up an extra variable in notation. Okay, so I'm going to run a similar algorithm here, but now with k counters and labels, and I'm going to get this stronger claim. Now this claim should look a lot like this claim over here, and maybe I have some equalities when I shouldn't, but if not, you can. So let's get rid of that. Okay, so now what happens if k is equal to if k is equal to 2? So if k is equal to 2, then this claim is that if something has less than half the votes, I can return 0, and I can return anything, right? If it's greater than half the votes, I have to return some count for this j, right? So I can, if k is equal to 2, I'm actually solving this majority problem. And you can actually, and I'll be a little sloppy with the analysis, and you can actually do this with k equals 1 counters and labels, but it's a little bit easier to think with k counters and labels. Okay, so we're going to kind of reproduce this algorithm, but solve this stronger claim that gives you actually a percentage error. So you're asking before if if I didn't have majority, I can return anything, right? This lower bound is pretty weak, right? Now is because essentially this was my lower bound. It was greater than the true count minus m over 2, and that happened to always be less than 0 if you didn't have a majority. So now I can tune this lower bound to be as tight as I want. Okay, so let's see how this algorithm is going to work. So we'll kind of, so I'll try and write up the algorithm, and then maybe we'll go through an example of how it works. But it's going to follow this same algorithm here. Okay. So, and again, you can think of the streaming algorithm just like a for loop. So if any, let's call this CT equals AI. So if any counter matches, sorry, this is the label. If any label matches our incoming thing, then we're going to increment the associated count. That's all we're going to do. So then the counter T, so that's the T is the label. So I'm going to now have a set of these labels, which is going to be L1, L2, up to LK, and these counters C1, C2, up to CK, and I'll use T as an index over these because I use I and J elsewhere. So, okay, so if I see something and I have a label for it, I increment the count. That makes sense. Okay. So else, if some CT is equal to 0, if some counter is equal to 0, that means I can take over this counter. I have nothing stored here. So now, if my only counter is equal to 0, I did this. Now, if any counter is equal to 0, I can do it. So I initialize all the counters equal to 0, right? So now I set the associated label equals to AI, and the counter T equal to 1. Okay, now else is the interesting case. So what should I do in this case? So you can see where my if statements are going. So now, if I have no label which matches my incoming thing, and all of the counters are storing something, now what should I do?
Decrement all.
Yes. Yeah, so you actually decrement all of the counters. So for all T and K, use CT minus minus. Right? So this is a kind of unintuitive step. Why do you decrease all of the counters when this happens? Well, it kind of turns out because it allows the algorithm to work. If you don't do this, then there are weird cases where it's not going to work. There's actually something else you can do at this step which will also work, which is probably less intuitive than this. Yeah.
So in this case, we can have some more than one CT that is equal to 0.
Yeah, afterwards you can have several of this counters equal to 0.
So when we are in the next step and we are in the else and some CT is equal to 0, which one of
You can pick one arbitrarily, it doesn't matter. Just pick any one that's equal to 0 and use it. Right, so the first thing you see in the stream, all the counters are equal to 0. Pick any one of them to use as the label for the first step. For implementing this, sometimes there's a little bit better choice for one or the other. You can actually get this to run in amortized amount of, so the constant time is, the amortized time for processing one element is constant. You need to check like if all are 0, and so you think it may depend on k, the number of counters, but you can get it so it's amortized constant by some careful choices in these places. But I'm not going to go into that. Right, so I'm going to decrement all the counters. Okay. All right, so this is the whole algorithm. And if I run this algorithm, it will solve the k frequent items question. Then at the end, if I have a query for fj hat, I look at all of the labels that I have. If any of them match j, then I return the counter as my estimate. It's always going to be an underestimate because I never incremented the counter too many times. Because I can only increment it when I see it, right? So this right side should be easy to see that this is true. The left side, again, is going to be a little trickier. And so now, okay, so now I'm going to give the argument, and hopefully you can go back and see why it works here afterwards. But I'm going to claim that I can only reach this step m over k times. So m is the total number of things in the string, k is the number of counters. Right? I can only reach this m over k times because every time I reach it, I'm removing something from my counter. I'm removing something from all the counters, right? In fact, there are k things. There are k things that I'm removing. Okay, so if I remove k things, and there are only m things total, I can only do this m over k times. Otherwise, I would have removed more things than I ever put in the counters. So I can only reach this step. This was only reached m over k times. Okay? So every time I do this, either I'm incrementing my counter or I'm doing this. So now I said I could do this with, there's, the reason this got a little tricky is because what's happening is I'm either incrementing it here, my counter for a label that I see, or I'm incrementing here because I moved from 0 to 1, or I reach this step. Well, I can actually pretend I have these k plus 1 counters. I can put it in, and then so I always increment it, and then I'm deleting it. Again, so then I'm removing, I can only do this m over k plus 1 times, actually. Then you can actually run it with k minus 1 counters as it elements. But if I only do this m over k times, I can only subtract a total of m over k from each of the counters. So that means I never underestimate by too much. Okay, so if you're doing streaming algorithms, so this was an algorithm by Misha and Gries in 1982. There's an algorithm that works slightly better in practice that's called the space-saving algorithm. That is, instead of decrementing all the counters, what it does is it swaps the label with the new label you saw when you reached this step. And then it adds one to that label. It's kind of a really strange thing, and it tends to work a little bit better. The problem with this is it really consistently underestimates the count. And if you kind of swap this step, then you have an overestimate instead of the underestimate, but it is more accurate in practice. So the space saving is often works a little bit better. So keep this argument in mind. So, I mean, this is solving this frequent items problem. What this says is every item which occurs much more than m over k, much more than if I use k counters 1% of the time, if it occurs 8% of the time, then I know it up to 1%. My guess of it is never less than 7% of the time. So any really frequent item I can find using this algorithm with a small number of counters. Okay, so we're actually going to come back to this algorithm in a few weeks and extend this to do some much more interesting stuff in a stream. We're going to show how to do principal component analysis in a streaming setting by kind of extending this algorithm. So I'll need to explain what PCA is and what it means first, so I'll delay this for a few weeks. And not exactly this algorithm, we need to modify it a little bit, but it's going to be a really cool extension. And that's something from just last year. It's a brand new ticket. And some of you have seen it already. Okay. All right, so do people kind of believe I can solve this frequent items problem now in a stream? So people actually, so AT&T invested a lot of research money into these sorts of problems, and they actually use this for inspecting for like denial of service attacks, and they calculate various other statistics on their routers using a lot of these techniques. Okay, I'm going to quickly describe a completely different algorithm for solving basically the same problem. So I'm going to again approximate the frequent items. So I'm going to do something called, so I'm going to solve the epsilon approx items. And so epsilon approximate, and I've slightly changed the name because I'm going to slightly change the bounds I'm going to get. The claim is now going to be that I'm going to return fj hat such that, so fj is always going to be less than or equal to fj hat. So I'm going to have no error on the lower bound, but it's not, I'm going to have fj is always less than fj plus epsilon hat. So now I've replaced 1 over k with epsilon here. So it's basically the same thing. So this is for, so epsilon is now my percentage. It's now in somewhere in between 0 and 1. So think of this as the percentage error I have. And so this is going to work, now this is going to be a randomized algorithm. So with probability 1 minus delta. So here before the space here was k times log n plus log m. And there's some big O with this. Now my space, and I'm not going to quite be able to use just counters and labels. I'm going to have space that's going to be 1 over epsilon, which was my k. And again, it's going to be log m log n times log 1 over delta. Okay, so now I have a little bit more space. I have a randomized algorithm and I have this log 1 over delta. I have a probability of failure. So say I want this to work 99 or 999 out of 1,000, so that delta is 0.001. Then this is log of 1,000. So maybe that's going to be log base 2 of 1,000. So that'll be, what was it, like 10. So I may need an extra factor 10 counters. This algorithm will have some. The claim is weaker, it's a randomized algorithm, has some probability of failure, and I need more counters. Actually, in practice, people actually set this, yeah, people often set this log over delta to something like 10. So this term in practice may be 10, or maybe even 5 would be okay. But it's going to have some nicer properties than this Michigree's algorithm. So this is going to be an algorithm called the count min sketch. And it's going to be even kind of less intuitive than this algorithm, but again, it's going to be very easy to implement, and we'll get these nice values. And so this was by Kormode and Luther Krishnan in 2005. Okay, so basically what I'm going to do is I'm going to keep 1 over epsilon times log 1 over delta counters. And I'm going to store them, instead of just in an array here, I'm going to store them in a table. So I'm going to set k equals to 1 over epsilon. And we're going to set something like s equals to log 1 over delta. And so I'm going to go from C11, C12, up to C1k, C21, up to CS1, and so forth, up to CSK. So I'm going to keep all of these counters and initialize them, all these counters to 0. This will be, okay, and then, so if I just keep these counters, it's going to be 1 over epsilon times log 1 over delta. I'm not going to get this term, it's just going to get the log m term. I'm going to need a little bit something else. What I'm going to do is keep a hash function now, h1, h2, up to hs. Okay, and each hash function, hi, is going to go from my domain to k. Okay? And each of these are going to be k, these s hash function are going to be independent. So these are going to be, and I don't think you need them to be fully independent, but let's not worry about that. In practice, it doesn't usually matter so much. Okay, so now the algorithm is going to be even simpler than before. I'm not going to have all these if statements. I'm going to have for a, I'll just see, a, for I'm going to do the counter. So I'm going to try and write this big. So the counter, hi of a so it's going to be, sorry, I comma hi of a, I'm going to increment this. Okay? And this is the whole algorithm. So there's one step here where I'm doing this. So basically what's happening, so let me go through it. So I'm going to have some element come in A, and I'm going to go for each of the hash functions. So for each of the hash functions, that's here, I'm going to hash it to one of the counters, right? So this is for row 1, I is equal to 1 here. I'm going to hash it to one of the counters. Let's say it hashes to this one here. And I'm going to increment this counter. Then I'm going to go to the next row. This is going to hash to a different one of these counters. It's going to be C2J. And this one may hash to this element here. So this is going to be, this is going to be one of these random hash function. So it's picking one of these counters at random. Now it's important, it's not just picking at random, it's doing by a hash function. So if I see the same element twice, every time I see it, it always increments the same counters. Okay? So now, but how do I return an element now? So how do I return something? So now I'm going to set fj hat equals the min of I in S of C I hash j. Okay, so to return this, so on a return it's a little bit, I don't just look up one counter, I need to look up all of the associated counters, and I take the smallest one. So this is why it's called the count min sketch, because I'm keeping the counters, and to return it I take the minimum. Okay, so I've got about 7 minutes to try and explain why this works. But do people understand the algorithm itself? The algorithm is very simple. At each element, you find the S different associated counters using some hash functions you've stored. These hash functions you can store each in about 1 over epsilon times log n space, as it turns out. So that's where the other space bound is. So you check each of the hash functions, you find the associated counter, and you increment it. Okay, so let's try and look at this bound first, and let's try and see why this left side works first, right? This left side has nothing to do with epsilon, so this should be easy. So my claim is that I never give an undercount. I never give a value which is too small. Why is that true? Why is this fj hat never too small?
The hash functions they're going to be collide. They're always going to have more than you really do because of the overlap.
Yeah, so I'm going to get some overcounts. That's true because of collisions, right? But it didn't exactly answer why I always get at least a count. It's not too hard. Maybe it's possible you're just overthinking. But it's because so let's look at some element that comes in, some element j. Every time it comes in, it always goes to the same counter, right? And I only increase these counters. So whenever I do a query, I look at all the counters.